Microsoft. Right, we are up and running. Okay, so I don't need to introduce myself. You all know me from, well, most of you know me from last year. I think there's probably a few people that don't. There might be a couple of Erasmus students. But we'll hopefully get to meet each other in person in the labs next week, which would be nice. I know we had a brief hello there on Monday, but it'd be nice to put the names to the faces. So this is operating systems. So I think I warned you last year when I had you that I would have you for this year. And, you know, similar sort of deal as last year. My advice is turn up, do the stuff, and you'll get through. If you don't turn up and don't do the stuff and don't keep up, you might struggle, okay? Because as you know, my CAs tend to be about what we do in the labs, and they're quite practical. Same this year. So I'm just going to give you a quick run through this, and then we'll do an intro deck, and hopefully we might do one other deck. So same as usual, video playlist. Anything I video will put on the playlist. If we go and have a look at that playlist, you should see at the moment that it has very little. Yes, all it has is the Google Cloud thing that we will use for Linux. Again, you could use anything you want for Linux, I don't mind, but if you do use your own thing, it is up to you to make sure you can download, upload, blah, blah, things to it during CAs and things like that. So if you're familiar with some other Linux environment, knock yourself out, off you go. My recommendation is use this, but it is up to you. Let's go back here. There's the Teams link. You got as far as here, so hopefully that's good. That's an interesting book. It's quite a large reference book, but it's not bad. So feel free to delve into that if you don't understand some of the stuff I'm talking about, or look it up yourself. There's loads of stuff out there in the big bad world. Just a little bit of information on Linux OS distributions. There's loads of them. For those of you who don't know, if you click in there, you'll find a little bit more information on that. Anything I do in the labs to do with OS, I will use Linux. I'm not a great Windows fan. And Linux allows us to demonstrate all the things we want to demonstrate. A couple of past papers there, all the rest are in the library or whatever. Be careful, I only set the exams from 2017 onwards. It was someone else before that. Some of the stuff is the same, some of it isn't. We will cover it when we do exam prep. But as usual, I always suggest you look at past papers as soon as possible to get a feel for the types of questions you will be asked on any particular subject. All right. These are the two we're going to try and do today. We may not get it all done because we've only got 40 minutes. I would ask you before the lab. So the labs are next Monday and Tuesday. So before we actually do the labs, please make sure that you're happy and refresh yourself with Linux command line, because that's what we will use throughout the whole thing. So do yourself a favor, do the little command line refresher. It's just that little silly, simple one. Make sure you're up to speed. If you're not, go have a little bit of practice. All right. That's, as I said, these are the same as I probably gave to you last year. They are two pretty good tutorials if you want to just come back up to speed. I don't go through them, but they're there for your reference. And that's another one as well, which if you're more advanced, if you're interested, you don't need really to know anything in that to do this course, but it's not bad if you want to have a play with it. All right, so that's what the Moodle page will look like. Obviously, as we go through it, you'll get more lectures, you'll get more labs and CAs, blah blah blah. All right. Okay, so let's go have a look at this one. If there's any questions, just flash them into the chat and we'll try to deal with them as we go along. We're up to 32. It's hard to get you out of bed this morning. Right, OS intro full time, blah, blah, blah. There we go. So let me just go, it used to be big screen. There we go. Right, operating systems. These are the boring slides that we do at the start, just to set the scene. But whether you like it or not, operating systems are everywhere. All right. Most of you will never, ever have to develop an operating system. Some of you in the software development may end up doing that, but it is a pretty niche skill. Because it's not, operating systems aren't written in high-level languages. They're not written in Java, they're not written in Python. They're usually written in C or C++, all right? So if you are actually good at writing that type of stuff, you can end up being, get a lot of money. because it's probably a dying skill to be able to write the operating system. However, you will all use an operating system and you need to understand how to best use an operating system. I'm in Erasmus. Send me the documents by email. I will, of course, yeah, Bastian. So as soon as this is over, if you send me a reminder email, please, and I'll send them back to you, okay? But obviously you'll have the video as well. You should be able to watch, but so you don't have access to Moodle, so you can't see the what you call it, the YouTube link, right? So you just send me your email address, and I'll send you out the link to the playlist and the document. Okay, no problem. Right. So as I said, they're everywhere, whether you like it or not. Embedded devices are essentially everything, like your smartwatch, your loads of gear in your kitchen, loads of stuff in your house, your router, anything that has a little screen or anything that has a little keypad or anything designed is essentially an embedded device. And guess what? There's a little OS running on it. And you know that in 20 years ago, that OS was some little proprietary thing that was handcrafted by the people who created that product. But now, a lot of them are actually cut down embedded Linux systems because those systems have become very cheap to put into those devices. And the reason why is, if you were to try and 15 years ago say, I'm going to design a device and I'm going to sell it for 20 euros and there's embedded Linux in it, you couldn't do it because you wouldn't be able to make the product for that price, right? Or for a price you could make money, because the chips were too expensive, the boards were too big, blah, blah, blah. Whereas now you can. And you want to tell me why you can do that now and you couldn't do it 15, 20 years ago? What changed? What has made all these things cheaper? Getting access to much faster processors. What made it all happen? What made it possible? No. It's more obvious than that. Memory size is very close. What drove? Why did big memory chips become cheaper? Why did expensive processors become way cheaper? What drove it? No. What does every single one of you have in your possession that you use every day? Yeah, mass production, getting very close. Of what? Phones. Exactly. Well done, Anthony. And what's the operating system in an Android device? Yeah. What's the operating system in an Apple device? No. Unix. Correct. All right. So all these devices are essentially using Linux or Unix, right? Linux is a close derivative to Unix, right? And if, as I say, if you tried to create this 20 years ago, you couldn't do it. It'd be too expensive. Whereas now, the mass production of those phones has driven down the price of memory chips, processors, everything is shrunk down. And if you want to actually go and make a device, whether it's a watch, any sort of sensor, anything you want to do, you can buy the bits and pieces, put them together, and it'll be quite small and it'll be cheap. But you can. Anybody got a Raspberry Pi? Anybody got one of those? Yeah. So what you pay for it, probably 10, 20 quid less. But anyway, you can. The main one I'm trying to get at is all these embedded devices now are, a lot of them are running really proper operating systems. They might be doing something simple, but it's actually cheaper to use those ones than try home grow or invent something, right? So it's everywhere from embedded, mobiles, tablets, servers, everything. And supercomputer, what's the OS usually? If you look up all the supercomputers in the world, what's the OS usually? It's used in them. It's Linux. Okay. So very, very powerful operating system, and they're everywhere. Everywhere, your Wi-Fi router, your projector, your an espresso machine, half of them, your washing machine, everything. All right. Okay. So that's just setting the scene there. It's very important though that you understand if you get an OS wrong, you're going to have a serious problem. All right. So because an OS is responsible for essentially sharing the CPU or CPUs, multiple cores, one or each or whatever, and it's responsible for divvying out all that great power and memory amongst all these programs, you know, the Excel, the Words, the browsers, the whatever, right, the Visual Studios. How do they all run in parallel, nice and quickly? Obviously, you need a lot of memory if you want to run a lot of stuff, and we'll talk about that in memory management. But if the OS is written badly, then the OS has what's called overhead, all right? And overhead is, in other words, any wastage, right? So if you write the OS really badly, your software is going to be slow in the OS. Therefore, you have less CPU time to give to the applications, and therefore that's a crap OS, all right? So it's extremely important that the OS is written properly and it's not a bottleneck to performance, all right? OS can actually also be an obstacle, right? Portability. How many of you have, you know, you come across, well, you see it every day where you've got, you know, an application that runs on, I've just got Windows versus Linux here, but, you know, you can just as simply write Android versus iOS, right? There's two major app stores in the world, Play Store and Apple Store, for iOS devices versus Android devices. And even though the application look and feel, take WhatsApp or something like that, looks nearly the exact same on the two devices, they're not portable, all right? Because underneath there's a different OS, there's different API calls. There's no Android in iOS. So portability can be an issue. So for instance, if you write something that works for Linux, it's usually very simple to get it to work for Unix, but it ain't very simple to get it to work for Windows. There are frameworks you can buy to help you along, and that is something you have to consider when you're picking which OS am I going to use, all right? And scalability is really, really important. This OS is brilliant on a single core, but actually when you add in multiple cores, which is multiple CPUs, it doesn't handle it very well. It doesn't scale very well. So you always want an OS that can do that. So for instance, if you look back at the history of Linux, it would have started out supporting single core. And then as processors, so you've probably seen the word things like octo-core in your phone or quad-core. That's how many CPUs are in there, right? So 5-10 years ago, there was one, then it became two. And octo is, I don't know if they've gone above octo yet. But it makes obviously OS extremely complicated because it's got to divvy out all the threads and processes out onto all those cores and handle them properly. So really, really important that an OS can do that. And concurrency is a fancy word for, what's concurrency? Fancy word for what does that mean in terms of processes running? Concurrency. Maybe you know what that means? Together at the same time, exactly. All right. So scheduling is basically, is there a solution for the chip shortage at the moment? Nah, above my pay grade there, Connor. But essentially, what happens is this happens every few years. You know, it can be the memory chips, it could be the processors. Usually it can be, you know, somebody goes out of business in the Far East, or a factory burns down, or God knows, or COVID problems. It's COVID is probably driving most of this stuff, right? They weren't able to get enough people in working to do the stuff. So it comes in waves. What happens is the price of the chips goes up, then it comes back. It's a nightmare if you're actually dealing with it. Have previous scars of that. So anyway, back to concurrency. Essentially, scheduling. It means scheduling is really, really important, right? And you did a certain amount of scheduling in first year with some of you did it with Mark, and some of you did it with Margaret, I think. It's a really, really important topic. We will revisit it to make sure that it gets into your pretty little heads. All right. Actually, I've just realised that I didn't do the other slide deck that I should have done before this, but that's fine. We'll do it in a few minutes. Just tell you a little bit more about the course. Where are we? Why study it? Okay, these are the boring ones, as I said. Very, very important, right? If you're in a company and you're deciding, you know, we're going to use, what are we going to do? We're going to build the computers, have them on premises. Are we going to use the cloud? What operating systems are we going to use? Are we going to use Microsoft's family of stuff, or Excel and Word? Are we going to use somebody else's? Are we going to use Macs? Total cost of ownership. What that means is the price of something is not just what you pay for the gear you buy. the price of it is usually also how much it's going to cost to support this over the next few years. How long will it last? All that type of stuff, right? Security features extremely important at this stage. Again, 5-10 years ago, no one gave a toss about security. Now it's extremely important, as the college knows after its ransomware attack. Scalability, as I said, I mentioned this already. What OS can I use to maximize hardware resources? As I said, the example is I have hardware at the moment that might be lots of just single or dual core. If I buy quad core or octa core machines, can the OS handle it, or is there a better OS to handle that? Okay, that's all. And again, if it's a high-end server, how many users applications can be supported? That's usually dictated by the amount of memory you want to put in the device at this time. But again, this stuff, all the waffle stuff. What features of an OS can I take advantage? You know, the kernel, low-level calls, pros. We're going to go through a lot of those, okay, over the next 2-3 months. So I won't really talk much more about them, but as I say, there's some interesting stuff coming up on memory management, process threads, concurrency. Okay, and they're just some of the issues, and they're the same issues faced, you know, in many areas of computer science when you go on. Like, for instance, I'm going to teach you a fair bit about a thing called synchronization. Okay, and essentially it's how do you make sure that if you've two processes or threads or whatever trying to access the same resource, be it a file or whatever, how do you make sure that they both can do it without corrupting the resource, the contents of the file, but they still actually get to work and they don't get locked out, all right? So that's a really important topic. It's very important in terms of OS, but it's also very important in terms of database usage, any application stuff. Anytime you have to access a common resource, and you have to make sure that, and multiple people are doing it at the exact same time, you have to make sure that that's done in an organized fashion, all right? And it's essentially synchronization. It's a really interesting topic, and hopefully by the time we finish all the exams as we do on it in a month or so, you'll understand it a lot better, and you'll understand the reason why it's important. Okay, as I mentioned some of this stuff, right? Traditionally, it was, you know, you wanted to do more, you added more CPU, you added a faster CPU. In other words, you bought a better computer, you bought a bigger or a faster hard drive, and you added more DRAM, right? That's essentially what you used to have to do. Now, people just, you know, spin up another VM or whatever on a machine or on some cloud-based thing, right? And again, you'll cover a lot of this, some of this with Martin as well. I'll mention a little bit about containers and VMs as well. But I won't delve into too much because he's going to cover it in his course. All right. Let me see. Again, multi-cores are now popular. So whereas before you needed to buy a faster CPU, now you just have multiple cores, multiple processors. So it's better. As I say, VMs and containers essentially have taken over at this stage. So I know you know a certain about them at the moment, but by the time I finish, you'll know a lot more. And that's basically just saying everything is quite important, right? Blah blah blah. What does an OS do? It abstracts the hardware. It abstracts the hardware from the users. Okay, so in other words, the user, he just wants to know whether he's using Excel or Word or Chrome or browser. He doesn't really want to know about the intricacies of how to manage the, you know, how much memory, what's going fast, what's not going fast. The OS is responsible to do all of that. All right. So that's the magic in the middle. It abstracts, a fancy word. It's just another picture of it. I'm not going to read that. You can read that. It's there's the hardware, there's the operating system, there's the application, there's the user. Okay. So in other words, it's abstracting the hardware from the layers above, and it has to deal with all of these things. And blah blah blah. That's the same thing. Intermediate. Blah blah blah. The OS is there's two views. Let's say this is real waffle stuff. Okay, the user view. In other words, the OS hides the hardware, and the system view. So a computer system has many resources. The CPU itself, memory, files, I/O devices, keypads, touchpads, LCD screens, Bluetooth chips, Wi-Fi chips. The OS has to manage all those, all right? And it's responsible to control all those in a nice organized fashion. So the user doesn't see any issues, right? All they see is turn on and off Wi-Fi, turn on and off Bluetooth. The OS has to do all the magic underneath to make sure that's done, because the Bluetooth chip might come from supplier X or it might come from supplier Y, and that's why you end up with things called drivers. All right, so I think most of you know what a driver is at this stage. I'm not talking about the one from golf. I'm talking about the fact that, as I said, if you use Bluetooth adapter X versus Bluetooth adapter Y, there's a different driver, but the user doesn't see any of that. They just see turn on and off Bluetooth. The OS has to figure out and load the correct software to talk to the correct adapter. All right, so it's all very complicated. And what's it do? Again, I'm not going to read these. You can read these yourselves, right? They're obvious. Execute programs, provide facilities like Visual Studio for actually how to develop programs, and I/O, let's say Bluetooth, for example. File system manipulation. Okay, so you take for granted that you click open or you look at your files and you see your all the files in your directory and all that sort of jazz. But what you don't realize is the actual file system that controls how they are stored can vary vastly in the OS, right? So in other words, the file system you would use, for instance, on a hard disk would be different than the file system you would use in on an SSD drive. Okay, everybody understands the difference between an SSD drive and a hard disk. You did it in first year, but essentially they're totally different technologies underneath, and they have to be handled differently as to how you write and read data from those devices. OS does that with a different file system. Okay, and if we have time, we might have a look at that. We don't usually delve into that too deeply in this course, but I might actually see if we can do it this year because it's an interesting topic. All right, but the OS has to manage all that. Communications, as I said, how do processes running on the OS talk to each other? We'll do a little bit of that. There are lots of different ways for if you write a process and you need to talk to another process. How do you get the message from one to the other? Very important is you have to, if something goes wrong, you have to detect it. The OS has to detect it and either tell the user something went wrong or clean up after it, right? Allocating resources. Memory is the single biggest one it's got to figure out, and we'll do a lot on memory management. Counting is essentially just logging stuff, all right? So people can see how much CPU is with this process versus that process. And you've all used Task Manager, so that's an example. And protection, which is really, really important. And that's where security comes in. In other words, how do you make sure that Pierce's files aren't viewable to Kira or Kelvin and vice versa? Okay, on a simple example, but there's a lot more. What interface does an OS typically present to applications? Okay, and they're called system calls normally, and they're written, as I said, in C or C++. They're not written in Python. They're not written in Java. Okay, an OS. Why is an OS written in C or C++ as distinct from Java? Yeah, much faster. Okay. And remember what I said, in an OS, you're trying to minimize overhead, okay? So therefore, you want the OS itself, when it runs, to be as quick as possible. So the main reason is it's faster, all right? There's lots of different APIs you could use, like Windows has one. POSIX is typically the one used for Unix and Linux systems. An example, if you're running a JVM above a real OS, it's a Java API, and Android is another example of an API. So the Java and Android one aren't technically OS APIs. They're layers that just sit directly above an OS, and applications typically would talk to a Java API or an Android API, which would in turn talk to the OS. Okay? That's the way those work. And they just, the last two slides on this deck, very, very abstract, very, very simple. Programmer views a computer as a mechanism to access, transform, and store. And I think we can all agree that's fairly true, right? Typically, you're trying to get at information you've got on the computer, or you're trying to get at information that is on the web or something, right? And essentially, there's two fundamental units, real theoretical bull this, right? There's a unit of computation and a unit of information, right? Computation is a process or a thread, and we'll talk about that later. So in other words, when I'm on the command line and I type ls, the ls is what's called a program, and when I run it, it becomes a process, right? In other words, it's running on the CPU. And then there's a unit of information. If I open a file, typically that's a unit, again, trying to get at a unit of information, right? Or some stream of data that may be coming from the web. A little bit abstract, right? Oops. Okay, so that's that one. I'm going to actually kill that video because I just want to do a separate video for this one. So I'm just going to kill that one.